Sorry. I think he can be molded by the institution. What's your other flag?
Next the and then
Already? Oh, because you have the research.
for this.
Yeah. I'm Robert. Is it Betty?
No. It's better
Yeah.
All right. I think we're set up. How are you guys doing today? Good. Hopefully you've all recovered from the exam last week. I have created a makeup exam which will become available after class tonight, and you have about 4 weeks or something to do it if you want to do that. And it covers the same things, plus I put a couple questions on tonight's stuff, analysis of variance on it as well. But let's get started. So I'm going to cover the bit of stuff on power and sample size that I was originally going to do last class and inadvertently put on the exam. You'll see tonight what would have allowed you to answer those questions, and then go over analysis of variance. This is analysis of variance. We're going to cover one-way analysis of variance just to get you introduced to the concept of it. This is a very, very extensive subject in statistics. You can take an entire course on analysis of variance at many places. It covers a lot of different types of studies. So here are the sections in the book, so you can catch over. It's actually not a whole lot of area in the book that we're going to cover, but they do have a section on each of these. So I just wanted to review this table that you've seen of type 1 and type 2 errors and power to get you back into the mindset of thinking about power. So we think of type 1 and type 2 errors in terms of the truth, which when we're doing an experiment, we don't know about, and the decisions that we make, the result of our hypothesis test, which is what we do know. So, whoops. Is that a question or is that just? I need to Q&A here. Okay, it's there. Good, we have 8 viewers. I'm just going to have to check back every now and then to see if there's a question, because I don't think. What's that? I wish I could, but I have not been able to figure out how to do that. Not in this room anyways, in the lab I have. But I will check and maybe remind me if any of you have a device or something that you could tune into YouTube on, you could let me know, but it doesn't matter. Anyways, so somewhere in truth, the hypothesis that we're testing is either true or it's false. And in relation to that, if we reject a false null hypothesis, that's no error. That is making a correct decision to reject the null. And the probability of that is called the power of the test, which is 1 minus the type 2 error. Whereas under the false null hypothesis, if we then fail to reject that, that's the type 2 error. So the type 2 error is accepting the null hypothesis when the null hypothesis was false. And whenever the null hypothesis is true, if we then reject H0, that's the type 1 error rate, the alpha that we've been learning how to control by calculating the p-value. And if we fail to reject it, again, that's no error. So far, so good. So this item here, the power, is what I'm going to talk about a little bit more today. And the key thing, so it's a well-titled term, power. You think of it as your power to detect a true departure from the null hypothesis. Increasing your sample size tends to increase your power to detect that departure from the null hypothesis. Less variability, less noise in your observations also tends to improve your power. Increasing your type 1 error rate, meaning that you're more willing to accept, to accidentally accept the alternative hypothesis, that will, wait a minute, is this right? You tell me, does this make sense? If you increase your alpha, your type 1 error rate, you make it more likely that you're going to reject H0, right? So then, should that increase or decrease your power? What's that? Decrease? Why should it decrease your power? You're more likely to give a false positive response.
So you get more false power.
So are you more or less likely then to give,
Power, like false.
you're making it more likely that you give a positive response. So power would be that your probability of giving a true positive response.
Alpha increases the sampling, the tails would get longer, right? Because it would narrow as alpha increases.
Well, the shape of your sampling distribution stays the same. Alpha just determines how much of the tails you're going to look at.
Well, so that's what I mean, right? So
right.
you can envision those ends like coming.
So you're see if I can draw on this. See if I can draw on this slide here. So if our sampling distribution under the null hypothesis is this, our rejection regions are like this. As we increase alpha, these rejection regions move inwards. Yeah.
I feel like that would increase your power, but I don't know why.
So how does this mean, that a false test comes out false, right? The higher power, the higher the false
Or
test.
a false null hypothesis it's the likelihood of rejecting your false null hypothesis.
That would increase.
Yeah, it is going to increase. So this, I think this is a mistake here on the slide. This,
Oh, okay.
yeah, yeah.
That kind of makes sense better than why.
Because your tails are getting bigger. And the tails, if something doesn't fall something falls on the tails, and that's when you're rejecting it,
So,
right?
so yeah,
So you're.
you reject more often. You reject more often, so your probability of rejecting whether or not your null hypothesis is true or false, your probability of rejecting increases as you increase alpha. So your probability of rejecting H0 when H0 is false also increases.
When I say false, we increase the power, does it make sense? Like, because it's not supposed to be the high power, but because you manually kind of increase the alpha to make the power increase, but truly it's not that high power.
So it's what you're right in that you're not changing the experiment. So what you're doing is you're improving your probability of detecting a change by lowering the burden of proof of that change. So you're more likely to see a small change or a difficult to see change because you are requiring less evidence. Yeah. So an alpha of 0.0001 is going to be very difficult to reject the null. You're going to have a low power to detect a difference with that high a burden of evidence, whereas you take alpha up to 0.05 from there, you're more likely to detect that difference and have higher power. Yeah, Leo?
How is power represented when people write up a report or something and tell us that something is significant and has this much power? And I feel like that can skew their analysis.
So the question is, how is power reported in reports and such?
Yeah.
The answer is it's usually not, and the reason is because power is ordinarily done before you begin the study. Power has to do with your expectation before you do the study. After you do the study, after you have the sample, it's not so relevant anymore. You've either rejected or not the null hypothesis. You don't base power calculations on the data at hand in a study. It needs to be estimated based on what you know before you analyze the data.
Okay.
Yeah.
So it's decided even before, like it's decided in the study design.
It's power and sample size are part of study design. And that actually, I think, is a wide misconception. I've been asked by reviewers and papers to say, what was your power to detect a difference in this case? And it's a question that doesn't totally make sense because it depends on what you knew before you started the study. It doesn't depend. You could use your current study to plan another study and say, what would your power to detect a certain difference be? But it really is it is an experimental design consideration or study design consideration. Yeah, question?
In a way that's reflected with alpha, correct?
In a way, what is reflected with alpha? What's your question?
Power is reflected.
So the question is, what's the relationship between power and alpha? There are equations that, and I have a bunch of plots here that I think will help make that clear. They are related, but they're not the same thing. Changing alpha will change your power, but they're different things. In terms of this table, alpha protects you against spurious positives, against false positives. Power protects you against false negatives. So here's a wordy example of when you might do a power calculation. So you're planning an experiment, and a very important question to know when you plan your experiment is, how big of a sample size do I need? So it is often expensive to recruit people into a study. You might, if there is some risk involved, you might unnecessarily put people at risk by going with too large a sample size. And in pretty well any case, having a larger sample size when you're going and collecting data costs something. So you want to have a sample size that's large enough, but you don't want to go overboard. So these experiments, these experimenters or these researchers, they're looking at self-reported pain on some quantitative scale, and they have an idea of what the normal variability on that scale is. And so they can use that estimate that they have of the variability, along with what they would consider to be, say, a clinically meaningful reduction in pain. So it might be that there's a very small difference just is not worth planning your study for. So that's another decision that is being made. And they can use those to then estimate how many people they need for this study. So does it make sense why these are the pieces of information needed? They need the normal variability, and they need to make a decision. So that's based on prior experience, prior data, and they need to make a decision about what is the size of the difference that they're interested in. Question?
This sounds like it relates to, figuring out how big of a sample you need to have a good study.
That's exactly what it is. How big of a sample size do you need to have a good study in order to effectively test your hypothesis?
Last class, you mentioned that the sample size of the study doesn't matter, doesn't affect your p-value or something else. Remember? That was kind of interesting.
That we shouldn't ignore studies that have really small samples because you can still get good results if you're, so sometimes people kind of throw the baby out with the bathwater and they're like, oh, this is only N20 or something, so it's not a good study. But that might not be correct. So I think we're interested here in
Yeah, so one of the things, the question was about one of the things we said last class, how in sort of the do's and don'ts of interpreting statistical analyses and studies is don't assume that because the sample size is small that the study is no good, or because the sample size is very large that it must be correct. And that still holds. In calculating this required sample size, what we are really doing is saying for a given hypothesized departure from the null hypothesis, how many samples would we need to see it? Or given a fixed sample size, then what would be our probability of seeing a departure from the null hypothesis of this size? So the noisier, the more natural variability that you have, or the smaller that difference, or the higher a confidence you want in rejecting, so a smaller alpha, all those will require a larger sample size. But it's context dependent. So, something where you have very little natural variability, you consider not that big of a deviation from the null hypothesis to be significant. You can do that with a small sample size. So this is the key difference between, one key difference between hypothesis testing and power calculation. As you all know by now, in hypothesis testing, we start with the assumption that the null hypothesis is true. And under that assumption, we calculate the probability of observing our sample or something more extreme in terms of the test statistic, which is the t statistic or the z statistic, or there are more that we'll cover, but that's always the way it works, is if your null hypothesis is true, what was the probability of getting our sample or something more extreme on this sampling distribution? Now, in power and sample size estimation, we're instead starting from the assumption that the alternative hypothesis is true. And then saying, okay, if this is our sampling distribution under the alternative hypothesis, then what would be the probability of rejecting the null? So it goes back to this table here, we're going to start out with this assumption that the alternative hypothesis is true or H0 is false. And then we're going to calculate this probability of rejecting H0 if we go ahead and do the hypothesis test. So that's a pretty radical difference, eh? Yeah. So let's see what that looks like. So I've drawn a bunch of plots here. These are sampling distributions. So, and they're drawn, I'm using a normal distribution here. So this is doing a z-test, either because we have a very large sample size or because the standard deviation is estimated from the population, or known from the population. So if here's a null distribution, it's centered on 0, standard deviation of 1, our rejection region with an alpha. So I put here alpha equals 0.025 because this particular tool I was using it just does a one-tailed test, but I wanted to do this for a two-tailed test. So the area under here is 0.025 for an alpha of 0.05. Now, if the null hypothesis is true, then the alternative distribution, the distribution of the alternative hypothesis is exactly the same. So it's the same mean of 0, standard deviation of 1. So if we assume that this is the true sampling distribution, what's our power, or our probability of rejecting the null hypothesis here? Yeah, times 2, because it's not drawn, but I'm going to count it over here too. The probability of rejecting it under the right tail is 0.025, and then another 0.025 under the left tail. That's the power. So that was the probability of rejecting the null hypothesis when the alternative hypothesis is true. In this case, it's just, well, 0.025 for a one-tailed test, 0.05. It's the same. In this case, your power is the same as alpha. Because remember, the alpha was the probability of rejecting the null when the null is true, and power is the probability of rejecting the null when the null is false. And in this case, or when the alternative is true, and in this case, they're the same.
So it's just the assumption at the beginning that's different. So looking at the null distribution or something like that, the null is true. You just prove that.
Well, the interpretation is that the null is true, because what power is power is the probability of rejecting the null when it's the alternative that's true. Okay, let's look at another case here. Now, the alternative sampling distribution is not the same as the null distribution. It's shifted over. I added in a difference in the means of 1.
Why did that happen?
Different reality. This is a different, say, this is a different experiment, a different, this is a case where the null hypothesis is false. So in the example from the exam of birth weight of SIDS infants, in the first one, it's where there's no difference between birth weight of the SIDS infants and in the general population. In this reality, there is a true difference.
This is based on your sample?
Yes.
Your ultimate?
So the sampling distribution is based on is based on the standard deviation and the sample size. But this shift in 1 here, this is just hypothetical. We're only going to talk about hypothetical for power calculation. So this is not coming from an actual sample.
That's your delta?
Yeah, so delta, this is a key quantity in power calculation. It's for a 2-sample test or for a 1-sample test. Delta is the difference in means between your null and your alternative hypothesis. So you can think of it as your effect size of interest. Yes.
To recap that, this is not from a sample. Basically, you're assuming that there's a delta.
Right. That's right. We're assuming that under the true null hypothesis, the difference in means or in z-scores for the middle of the distribution is 1. So with this being the difference, what is our probability of rejecting the null hypothesis? So now the alternative distribution is true because we've assumed that it's true. We can calculate the probability of rejecting the null as the part that is above, because when we go and do the hypothesis test, this is the distribution that we're going to be looking at, right? The null distribution. So this is the rejection region, but here in our hypothetical world, we know this is the real distribution, and we can calculate this probability here. There is obviously a rejection region over here too, but this probability now is going to be very small. There's going to be much less area. Yeah. So the power here is approximately going to be just the area in this right tail here to the right of the rejection region.
Is this 3.05?
Yep, this is still an alpha of 0.05. Because this should have another rejection region here. I should go and draw them in.
Wait, are you saying that all of 0.05 is now contained in the right tail?
No, this.
You're not saying that, right?
No, this area here is to the right of 1.96 is 0.025. Yeah.
But in the bottom graph, if you shift it, that wouldn't work.
What do you mean if I shift the bottom graph?
Yeah.
That's what I was thinking too. Like it's not just the right tail, you're gonna have the left tail too. But it's not because it's shifted over.
Yeah, so here, there's going to be, so this is actually should be at 1.96. There actually is a minuscule bit of probability here too, which is part of the power. That part gets, if you do a hand calculation, you neglect that part because it makes it more complicated usually, and it doesn't contribute very much. I mean, if it does contribute something, then you're going to have a very low power because it means there's a lot of overlap between these two distributions, like in the in that first case. Yeah, question?
Power, we increased that from 0.025. Is that better?
Yeah, so the power here is better. It's now, what is it, 0.169. It's still not great. But that's this area. You can see there's more area under this tail now. What's that? Well, let's look at the next one. So now I've increased the difference. The difference is still 1, but what did I change here? Standard deviation of 1, n equals 1. Oh, I increased n to 10. So that decreased the standard error in these sampling distributions. And we're starting to get some respectable power here. We're up to 0.885. So that would be called 88% power. So do these two plots here, does this make sense what the power means in terms of these two?
So it's rejecting proper cases, more proper cases, I think.
What do you mean by proper cases?
Cases that should have been rejected were rejected at a better rate than increased power.
Yeah, cases that should be rejected are being rejected more frequently due to high power. So here the assumption is that this alternative distribution is true. So this is the actual distribution of samples that we're going to get. And about 88% of them are going to be out in this tail.
Essentially, 88% of their subjects will qualify.
Or not of your subjects, of your samples. Yeah. Yeah, in this case, yeah.
Is that the alpha is increased, so the power is increased?
Alpha's the same.
But
Yeah.
why there's 0.619?
Their sample size is bigger.
Right. So this was when n was equal to 1, the rejection region was 1.96 here because it was standard normal. But now the standard error is 1 divided by square root of 10. So it's the rejection value here of the z statistics is 0.619.
So the alternative kind of fits this way in that.
Sorry?
So the section that's blue for our alternative, that's kind of what would fit into the red section of our null distribution, essentially.
So the blue section is saying, okay, when we do go and do a hypothesis test, we're going to assume the null hypothesis is true. Here are the regions where we will reject the null hypothesis. But if we assume that this is the true distribution, this alternative distribution, what is the probability of getting a sample that actually lies in those rejection regions? And that's what the blue is. That is the area under this hypothetical alternative distribution that falls in your rejection regions for the hypothesis test. And it's easiest to think about, well, a lot of power testing is done under the assumption of the t-test. So this is not that limiting what you're learning about here. This is the way it gets. I mean, you can do power tests for all kinds of statistical tests, not just z-tests and t-tests, but they're the most commonly used. So making another change here. So here is still n equals to 10, but I changed this difference to 2. And so the rejection region is the same, but now almost all of the area under the alternative distribution lies in the rejection region. So our power is up to close to 100%. Yeah, it's going to be 0.9999999 or something like that.
So this would be an example of a good test design?
Well, this is a very high-powered design. It's saying this is a difference that is probably so obvious that you only need n equals 10 to do it. If you went and did, collected n equals 100, you'd probably be wasting resources. So yeah, I mean, you might be able to even go with fewer than n equals 10. You're not gonna, a case like this might happen in like a laboratory test or something like that. Most likely, if this is an experiment involving people, you won't have 100% power with a sample size of 10, most likely, but you never know. But yeah, this is an example of a more than adequately powered test.
Is that what you aim for?
Usually you aim for 80 or 90% power.
So
That's,
when you say this is more power, it's more power of what?
it's more power to detect this, to detect an alternative distribution that looks like that.
A true alternative.
Yeah, it's saying if this hypothesized true alternative distribution is the case, what's our probability of rejecting the null hypothesis? Mm-hmm.
So say like we have a different study. One is like have power 80%, the other one is 90%. Is that the power you're talking about?
Sorry, could you repeat the question?
80%?
80%?
Power, 90% power.
Mm-hmm.
Is that the same power you're talking about here?
Yeah, so in the exam, there was a question about 80% or 90% power, or if you ever hear 80% power, this is the power that they're talking about.
So I thought like if you have 90% power, right?
Mm-hmm.
Your P is more statistically significant in the test results, right? And your alpha is off. So your type 1 error is less.
So you're talking now about alpha and type 1 error, and just keep in mind the distinction that when you do that, hypothesis testing is something that you do on your sample. Power analysis and sample size calculation is something you do before you have your sample. Because in study design, because these, we're looking at the distribution of all samples. If you were to go and repeat your study 1,000,000 times, we're saying if the null hypothesis is true, this is the distribution of means or whatever sample statistic. And if our hypothesized alternative distribution is true, this is the sampling distribution. So we're doing this calculation prior to collecting the sample. So
the purpose, you set the power first, and then you use the power to calculate the sample size needed.
Yes.
For the
So
study design. Is that what you're doing?
yes. So it's a clarification from the audience of what the power is for, and it is for study design, and it's for estimating before you take your sample and do your analysis, what is the probability that if there is a true difference, say in the sample means of some given amount, what's the probability that will correctly reject the null hypothesis?
What detect the true alternative hypothesis?
Right, the power to detect a true alternative hypothesis. So here is an all-purpose power formula for all of the tests. This can be adapted at least to all of the tests that you've done so far. And it's based on these plots. It's this difference in mean divided by the standard error of that difference in means minus, it's the difference, in this case, 2 minus 0 divided by the standard error, which is, in this case, it's 1 over the square root of 10, and then minus, so that gives you a value of z and then subtracting the value of Z for your null hypothesis. And then here's some how you can go and apply that formula to each of the different types of tests that we've done so far, to the 1 sample for means and proportions and 2 samples with means and proportions. And these are just for Z tests here. Yes?
So going back to that last plot,
Yeah, the last plot.
the alternative, it's all on that side of the rejection, so that's too much, it's more than necessary. for
Right.
A successful study.
Yeah, so this is more sample size than necessary for a successful study here, assuming that this, that our difference in means actually is 2 here. One of the, the catches of power analysis and sample size estimation is that normally you don't actually know, you haven't done the experiment, you don't know how big this difference is going to be between your null and your alternative distributions, and you don't necessarily even know what the sampling variability is unless you have some pilot data or prior data to work from.
It just sounds like an assumption of how much work do you think you can possibly do with your staff? What is an abuse and what's the logical number to get some results?
Yeah, it's based on some pretty heavy assumptions, power analysis. But if you're going to go and spend a lot of money on doing a study, it's things that you should think about anyways, even if you obviously there's going to be a lot of assumption behind any power analysis. I'm not going to go into these too much. There are also, when I've done power analysis many times, I ordinarily use the software. It means you're less likely to make a mistake putting it in, and it's also then just as easy to do it for t-tests as it is for z-tests. I forgot about that build there. Here's a simple. What's that?
That would have given the answer.
Yeah, that was the answer you were looking for on the test. Yeah, they're right here in the lecture. So the most useful thing I think in these formulas is just to give you a reference point for remembering what effect these different things have on your required sample size. So that difference in means is the sample size is inversely proportional to the square of it. It's also proportional to the square of the standard deviation of your individuals in the population. And then to the square of your critical values of Z under in the null and the alternative distributions.
So delta is difference in means, right?
Yep.
Of the samples, so the sampling distribution, like X bar?
Yes, that's right.
Right.
Difference. Well, they're remember that your X bar is an unbiased estimator of the population mean. So this actually is, since we're talking about the true null hypothesis and a hypothesized true alternative hypothesis, this delta is really the difference in population means. Because you haven't even done the experiment yet either. So this is really the difference in population means. This is a population standard deviation.
But you're saying that because we assume that sample mean is closer to the population mean, right? Because that's the assumption in the normal distribution.
Well, the central limit theorem, it says that the average value of the sampling distribution is the same as the average of the population distribution.
Yeah,
So if you have a large enough sample, the means are the same. Or if you take many samples and then take the average, then the mean is the same. So this ratio, this delta to sigma ratio, is something that you might hear sometimes referred to as effect size. It's like the ratio of the difference in means divided by the variability. So you could think of this as being inversely proportional to the square of an effect size, where the effect size is that ratio.
Is that, Z score for beta is the previous ID power with the difference over standard error of difference minus, type 1 error? What's the beta power, Z score?
So this was a way of calculating the power of getting the critical, the value of Z that you could then look up on a table to get the power to calculate that. So this would give you a value for Z that you could look up under the right tail of that would give you your power. This equation is just saving you some algebra to give you a direct way to calculate the sample size to achieve that power. Z beta and Z alpha are the values that I was showing on the plots earlier.
That was the 0.67.
Right.
Then, so I was gonna say, was delta given to us? Or was delta something we had to figure out?
In those plots, delta was given to you. On the exam, it was given to you, and the question was to calculate sample size. It was this equation.
So 0.67 for the Z's.
Yeah.
We had the standard.
Yeah,
deviation.
that's right.
It's so simple now, yeah, right? That's why I said that for an hour looking at it. It's just like, really?
just maybe,
Uh-huh.
are alpha and beta the same?
No, alpha and beta, so alpha would be, say, 0.05, beta would be something like 80% or 90% the power. So if you wanted to know the sample size required for 90% power, you would put that 0.9, look up the Z for 0.9, you would look up the Z for alpha, or for 0.05 over 2, you would plug those two values in, and you'd use your standard deviation and difference in means. Yeah, question?
So, to get the Z power, you just like that, the standard error, right? Do the calculation of this with the slide.
Yeah, to do the power calculation, you need the standard error.
But to get the standard error, you need the sample size, right? But it's like
And to get standard error, you need the sample size. Yeah. There are 4 things in a power calculation. There's sample size, alpha, beta, and this so-called effect size, the ratio of the difference in means to the standard deviation. If you have any 3 of them, you can calculate the 4th. And sample size tools that help you to do it will work that way. You just specify any 3 and it gives you the 4th one. So you can do it either any or either way.
Wait, so Z beta is calculated from that Z power equation, right? Can you go back? That one?
It's the first part of the equation, the difference over standard error difference.
Yeah.
That's Z beta.
Yeah.
Oh,
Because power is 1
So for
gotcha. Sorry.
Thank you. Yeah, this first part, oh shoot,
Yeah, they're all on one side.
is Z beta.
The table.
I'll make up a summary slide of these, even though you don't need them on an exam anymore. But they're good. But they're good to know. They're good to know. Most statisticians, a lot of their work isn't doing power calculations. It's the most commonly requested service of statistics cores. People want to know how many samples they need when they plan their experiments. What about consultancy rate?
Is that like, you get paid by consultancy rate for calculating that stuff? Or
Oh yeah.
you get hired per job?
I don't know, what's the difference between per job and consultancy rate?
Essentially, you just calculate it once, and you're like, good to go and pay.
Yeah, that's right. I mean, you know, probably most of the work is in trying to figure out what the assumptions are that you need to calculate a power, but the actual power calculation doesn't take long after you've done it once or twice.
The power of knowledge.
Very good. It's the power of knowledge. Okay. Okay, I'm going to skip over all this stuff we've been discussing a lot. Remember to get rid of these builds. Okay, I'm going to kind of gloss over now so that we can move on pretty soon. Oh, I should check for questions too. 105, doesn't look like any questions. So the key thing here, I think, is this: given any three of alpha power, sample size, and delta, although really you also need the standard deviation. So the ratio of delta to standard deviation, you can calculate the fourth. Factors that increase power, obviously increasing that effect, that difference in mean increases your power, decreasing the standard deviation, so increasing that effect of separation, that increases your power. More sample size. Here was the answer to that other question. For two samples, the small of your samples is the one that limits your power. And you have, for a fixed total sample size, your power is best when you have them equally distributed across your groups. And that'll go for 3, 4, or more groups as well, but it's the case also for 2 groups. Reducing, I got it mixed up here. This is obviously a, well, it depends on what you mean by reduced significance level. So increased alpha, that's true, will increase your power. All right, what time is it right now? Almost 6. So we're not gonna, I'm probably gonna have to do, okay. I'm going to go through some analysis of variance. I know that's going to be this is going to be the topic of your lab tonight, so I want to go through some of it, even if we have to go through it kind of quickly. Analysis of variance is something we can use when we have more than 2 groups. We've covered 1 group, we've covered 2 groups. Analysis of variance, a one way will be when you are comparing the means of 3 or more groups. And it's also for a lot more than that, but that is kind of the most basic application of it. And it's a different approach than the t-test. So remember the cell phone example where we're comparing cell phone users to controls who are not using a cell phone. We used a t-test to compare that. We also used a paired t-test. If we were to add another group to that, so voice only and voice plus data, that would then be into the realm of analysis of variance. Let's talk about another example though. So an evaluation of training programs to see if several different teaching methods or learning methods result in a difference in learning time. So here's a very, very small study, just 3 observations in each of the groups for 3 different methods, the research question here would be, is any one of these methods different from any other method? Notice it's not about which of the methods are different, only that some difference does in fact exist. So if we were to do an analysis of variance here, we would calculate the mean of each of those groups, a standard deviation within each of those groups, and we would be comparing these means. And the question is, are these sample means consistent with the null hypothesis where the true means are all the same?
Do you need a control for that? Like, is one of these a control?
Do we need a control for that? In this case, presumably one of the methods you could think of as your control. That would be like your standard teaching method, and the other 2 would be alternatives. But it's not strictly necessary for the analysis of variance. What's necessary is that there are groups to compare between. So they could be 3 different treatments, and you're wondering if there's a difference between the treatments. That actually is a common case in like drug tests where for humans, where it would be unethical to give someone no treatment, but it may be ethical to give them a standard treatment and then give them a standard treatment plus additional care. So as long as there's some comparison to make.
Because you already have data from the standard treatments. You already know how the standard treatments go.
So
or you're assuming within your experiment that the standard treatments.
So you already know something about the standard treatment, but still ordinarily when you do a study, you would want to look at standard treatment rather than just relying on historical data, just to make sure that your groups are comparable, because you've done your study in exactly the same way in every other respect. This, by the way, is an analysis of variance table. You'll get used to them over the course of your degree here. You'll see lots of analysis of variance tables. Here's a box plot of this hypothetical little experiment, the method 1, method 2, method 3. So it's only a sample size of 3, but there's a pretty big difference in this 3rd method. So maybe that's inconsistent with the null hypothesis. We'll see. So why not just do all of those pairs of tests, right? You could do it like this: method 1 versus 2, 1 versus 3, 2 versus 3. One reason not to do that is because the more tests you do, the more you tend to increase your type 1 error rate. If you don't control it in some way, then even under your true null hypothesis, you'll start becoming more likely to reject the null, just due to random sampling variation. It is possible to correct for multiple testing so that doesn't happen, but if you do that, you're going to end up with not as powerful a test as the F-test and analysis of variance. The analysis of variance F-test is the best test to do under this situation with normally distributed population data. So I'll leave this for you in the test. This is just saying the same thing again. This is that inflation of type 1 error rate. If you do 3 tests, your probability of accepting the null each time is 0.95. The probability of accepting all 3 of them would be 0.95 to the 3, and the probability of rejecting at least one of your nulls would be 1 minus that, and it works out to 0.14. So even under a true null hypothesis, if you do 3 tests with an alpha of 0.05, your actual probability of a type 1 error is is 14%. And that just keeps on growing and growing as you do more tests without some kind of a correction. So the basic idea is similar to some of what very random sampling variation. And the same difference in means, if you have a greater variability in each sample, might be more likely to come under the null hypothesis than if you have less variability in the individual data. So this would be less likely to occur by chance with no difference in means. You can look at that also on a density plot. This is the same thing, just another way of looking at the data. If these are 3 population distributions here, you can see that there is some difficulty in distinguishing these first 2, maybe, and less difficulty distinguishing the third one. And what we would actually observe as we did the sample would be, if these are true, it would be a sample taken from each of these, and the larger the sample we took, the more it would start resembling the population distribution, and the more clear it would be that they are different, as we see in these density plots. So before we were working with either just 1 mu, 1 mean, or 2. Now we have any number of them, the number of groups G. We have a standard deviation, potentially different for each group. These are for the population. The sample statistics, these should be like an X1 bar. I don't know why this didn't show. X1 bar. Like that up to G, and standard deviations. So same terminology, we just have more of them. Our null hypothesis is just a review of our 1 and 2 sample tests. Under the analysis of variance, it's now just that all of these group means are the same. So, and the alternative is just that they're not all identical. There's some departure, but no statements about where that departure occurs. Sound good? Sound useful? Yeah, it is useful. Here are the assumptions that you'll need to make to do an ANOVA. One is that your population data are approximately normally distributed, or that your sample size is large. ANOVA is very robust to departures from normality. So if you have a sample size of greater than 40 put here, then it almost doesn't matter what your population is like. For smaller samples, like less than 15, then it does matter more.
Which would be in contrast to the t-test.
What do you mean in contrast?
Like I think it's just fresh in my mind because I got clear with you about it the other day that like when we're doing a t-test, we have to assume that it's normally distributed, but with an ANOVA, we don't.
No, it's an assumption. So the normal distribution is an assumption both for the t-test and the ANOVA, and also for both of them. As the sample size gets large, that assumption becomes less important. Yeah, it's for small sample sizes that assumption is important. And I think there were, at some point, I gave some rules of thumb for sample size with t-test as well as to how important the assumption of normality is. But it is an assumption, and it's the derivation of these is based on a normal distribution in the population. By the way, there are tests of normality, and you might see in some places a suggestion that you use one of those tests, like the Levine test, to see whether your data are normal before doing an F test. In the introductory statistics book that I used back in the day, they likened that to sending out a rowing skiff onto the ocean to see whether it was calm enough for an ocean liner. that those tests for normality, they're very sensitive, and they will detect small departures from normality that just don't matter for the F test. So, yeah.
So what variable do we get when it is a significant difference?
What's that?
So like what do we look at, say we run an ANOVA, what value tells us that, yeah, there was a significant difference?
Right, so what value tells you whether there's a significant departure or not? It's gonna be just what you're used to. You're gonna either get an F statistic and look up the critical value of F in a table, or you're gonna get a p-value from your software, and that part of the testing is gonna be exactly the same. Usually, you'll make this assumption of homoscedasticity. It's actually not strictly necessary when you're using software. So I should say a possible assumption. If you're working with a very small sample like that one with 3, you're going to make the homoscedasticity assumption because you don't have enough data to really assess it. And in pretty well all cases of these assumptions, the F test for ANOVA is conservative when violated, meaning that if your assumptions are not violated, your p-value will get larger. You're less likely to reject the null hypothesis. So you're very unlikely ever to incorrectly reject the null hypothesis with ANOVA. And as with all statistical tests, we make the assumption that our data are they come from random sampling or from a randomized experiment. So these are the 2 key values that you need to do an F test if you're going to do it by hand. One is the standard deviation within your groups, and this is just going to be a weighted average. So you would calculate your standard deviation in group 1, group 2, in each of them. You multiply them by, anyone know what n-1 is? Degrees of freedom. Yep, the degrees of freedom for each of these, and then divide by your total degrees of freedom. And your standard deviation between groups, which would be a similar calculation, but just using the, this is the mean for, this is the mean for the group divided by the overall mean. And in this case, just weighted by the total number of samples in that group. So you could imagine in this plot, where was it? In this, the withins, that's what you see here. The between group would just be 3 points here, here, and here. And it would be the standard deviation of those 3 points weighted by the number of data points in each. So that all of the variability you see in your data is going to be attributed either to within group or between group variability. And the key idea behind the F test is that under the null hypothesis, your ratio of these 2, so the ratio of between group to within group variability, will follow a known distribution. That's the F distribution. And so if you have a big difference between the groups and little variability between them, you're going to get a large value for F. And this is a one-tailed test because any way that the difference occurs will result in an increase in the F statistic. You can never have a negative F statistic, and you don't even get values that are very close to 0, because if you have within group variability, you should have some amount, a comparable amount of between group variability, even under the null hypothesis. This is what the F distribution looks like, and it depends on your so-called numerator and denominator degrees of freedom. The numerator degrees of freedom, so that was your between groups, it's your number of groups minus 1, and your denominator n minus the number of groups. So this has to do with the number of degrees of freedom inside your groups, and this with the just the number of degrees of freedom in calculating your standard deviation of the groups, so of the group means. And the F distribution changes with both of these, but it's in general just this asymmetric skewed distribution that's small near 0, increases to some peak, and then has a long tail to the right. And in all cases, the rejection region will be off here to the right. So this is familiar. You remember drawing tails, calculating a critical value based on your alpha. You chose an alpha, you looked up the critical value in a table, and then if you got some statistic more extreme than that, then you reject the null. And it's even easier with F statistic because you will only ever look at one tail of it. You will never look at the left tail. Actually, as a side note, people have looked at the left tail, and they have done it to identify academic fraud.
Oh.
That's pretty useful.
Yep.
Wait, what do you mean?
So imagine that you were falsifying data. You've got a control and an alternative, and you don't want there to be a difference between them. You know, so you invent your data with very, very similar means, maybe almost exactly the same mean. If they're too close, you end up, you know, with it being very, very unlikely that your two groups would actually be that similar. You've invented data that are too similar. And that's when you might use the left tail of the S distribution. It would look like, if we looked at those box plots, it would look like two boxes that had, say, large variability like this, and just a minuscule difference between them, such that your sampling variability should have caused more of a difference than that. Yeah,
Good to know.
it's very difficult to falsify data that somebody couldn't figure out was falsified.
Because what was it? The Teach for America in New Orleans, they falsified their data for outcomes of students.
Did they?
Yeah, and then they just fired the dude.
Huh.
Somebody caught him using this thing.
Or something, yeah.
It's good to know, like, how do you find out? Because it was
Yeah.
found out like a year or 2 years later or something like that he'd been doing on a couple of reports.
I will check that out.
All right. I think it's, yeah, 6:15. I think let me just check here. I think I've given you enough to know what's going on. Yeah, you'll get more chance reading the analysis of variance table. It tells you the things we've talked about, your numerator and your denominator degrees of freedom, your total sum of squares. These are residuals or differences between in your between groups, it's the group means minus the overall mean. In your within groups, it's the individual data points values minus the group mean, an overall value of F and a significance value. So, but you'll get, what's that? Yep. So even with the sample size of n equals 3 in each group here, it's a significant difference. So, yeah, some post hoc tests. Read this on your own. The post hoc tests are something that the software will do for you. You'll probably do the 2 keys method, and you'll get some practice doing that tonight. All right.
About like stuff that's due next week.
Mm-hmm.
Introductions for the.
Oh yes. So the final project, I found some fun data for you. It's Ebola outbreak data, and looking at the mortality rate as a deaths compared to number of cases in a bunch of different countries where there have been outbreaks. I set it to become free, I think this afternoon, so you should be able to see it already on Blackboard. I actually included another data set, one that I used last spring that was flu shot vaccination in New York City, not as exciting, but basically I want you to do a project that you want to do. If you have other data, you're very welcome to use them, or if you find other data on the internet you want to use, you're very welcome to do it. It does not have to be the same thing. I tried to pick out a couple interesting ones for you to do if you don't feel like looking around and finding your own project. But yeah, there are some sort of milestones that are on the syllabus for completing it. Those are really to help kind of guide discussion. We'll have discussion on the Google group, and I'll talk about things about it as we go along. I'm not going to grade those initial submissions. I will consider them that you've made them as part of your class participation, but the thing that will be graded is your final product and your presentation, which will either be on the 22nd or, as I mentioned in the assignment, if you want to do it the week before that so you can travel or whatever for Christmas, that's fine too. You can do it on the, you can finish, I think it's on the 15th. So, but just let me know so that we can plan for the number of people presenting at which times. Okay, let's get downstairs, and so Tony isn't so lonely.
Actually, I'm listening earlier because my education reimbursement from the work, they